cis and trans isomers. I have a new lesson for you about cis and trans isomers. This is the most commonly asked question. What are isomers? And they are harder than regular organic compounds because they require visualization of the molecule and rotation along its axis. So let's look at what they are. Cis and trans isomers are geometric or configurational isomers. Configurational isomers meaning their configuration is different, right? Their structure is different. That is why it's called geometric or configurational isomers. In simple words, they are organizations of atoms that alters the shape of the molecule. This is possible when the atom cannot rotate freely due to the bonding with the rest of the molecule. For example, I have one below here where I have carbon bonded to the hydrogen, chlorine, and bromine. Now, because carbon has 4 as its bonding capacity, it bonds with 4 different things, it forms a tetrahedral structure, right? So because we are not living in a 2D world, we exist in 3D world, when a carbon attaches to 4 items, it is not to the left, right, top, and bottom. It's actually more of a tetrahedral structure where we have one on the top and one on the side, one behind, and one coming forward, right? So this is more of a tetrahedral structure. So it's not up, down, left, and right. Okay, so that's very important because if it was up and down, left, and right, the angles between all the bonding pairs would be 90. But if you place them in a tetrahedral configuration, it will be about 109.5 degrees apart. All of the bonds from one another will be 109.5 degrees apart, which is further away than being only 90 degrees away from each other. And therefore, a carbon with 4 bonds will exist in a tetrahedral configuration. Right, so once we have cleared that, let's look at an example here. So I have carbon bonded to the hydrogen, chlorine, and bromine. And I have highlighted the bond from carbon to the big chain or major chain, whatever the parent chain is. So since carbon is linked to the main chain with a single bond, this molecule can rotate. And if you see the next one, I have rotated the molecule where chlorine is on top, bromine is behind, hydrogen is forward, and then I have rotated again, and bromine is on the same page, hydrogen behind, chlorine forward. So since it's only connected to the chain using one link, one bond, one prong, if you want to, it can easily rotate, and therefore these 3 configurations will not be considered isomers because this bond can rotate. So how can we have these cis and trans isomers then? Well, let's look at another example here. Now if you see, I have 2 bonds between the carbon. 1, 2. And now if you again recall, carbon can have a bonding capacity of 4. It is using 2 of its bonds to connect to the next carbon. Because 2 of the bonds are being used to connect to the next carbon, now the other hydrogen and the chlorine on the left hand side, this hydrogen and this chlorine, cannot rotate. The molecule cannot rotate anymore. It is fixed in this position. And this is going to be a trigonal planar shape from the perspective of the carbon. So since the molecule cannot rotate now we can have 2 different configurations. In other words, if the molecule is given to you as a molecule on the left hand side, that has to have a different name because it has different properties than the molecule on the right hand side, because the carbon cannot rotate. The hydrogen in the first molecule on the left hand side is on top across a double bond, and on the second molecule, hydrogen is on a diagonal. So if we can look at this, I'm going to switch colors here to show you. So the way the naming happens is we are looking at the carbon chain. If it is on the diagonal or high priority groups, where are they located? So in the first case, we have a higher priority group at the bottom, across, and at the bottom. So both the groups are on the same side, below the double bond, below the carbon, same side. And this is considered a cis configuration. Cis means they are both on the same side. It can be both at the bottom, both at the top. It doesn't matter. It is on the same side, and therefore it's considered a cis configuration. It's a cis isomer. On the second molecule, what we have is we have a high priority group here, across the double bond, and down here. If you see, the high priority groups are on a diagonal, and therefore this is considered a trans arrangement, right? So it's a trans isomer. So we have a cis isomer where the high priority groups are on the same side, and trans isomer, the high priority group are on an alternate side. Why is this important? Well, as I said, I hinted earlier, this affects its properties. Because in the first case, in the cis isomer, the high priority group or more electronegative group are on the same side, they are being forced to be closer together. And therefore, the molecule is less stable. And in terms of biological terms, it is going to be easier to digest or process or break down. And so therefore, cis isomers or cis fats, for example, are better for us. And the other case, second one, we have trans configuration where the chains are going to be on a diagonal. So in a fat, for example, trans fat, this is going to be much more stable, and it will take harder time, or the body will take a harder time to process this kind of fat, for example. And therefore, that's why on the packets of chips and boxes you will see zero trans fats. Zero trans fats does not mean it does not have any fats. It just does not have fats that have trans configuration. It may have all the saturated fats it want to have, but it will not be trans fat. So they can still label it as 0% trans fat, even though the substance may contain saturated fats in it, or cis fats in it. Okay, so that is the idea behind cis and trans isomers. I have one more example for you for cyclic compounds. So the same idea can be applied to cyclical compounds. Because if you look at the carbon is right here. It is linked to, sorry, I'm going to be specifying on these two carbons here. It is linked from 2 points. And since it's connected to 2 points, it is not free to rotate, right? So since it is not free to rotate, the positions of the branches, in this case hydrogen and the bromine, on both the carbon atoms are fixed. They can't rotate. And therefore, the diagram that I have on the left-hand side and the diagram I have on the right-hand side, these configurations must have different names. So how do we tell the name? Well, let's go for it again. We have hydrogen sticking out at the back, or sticking at the back right there. So in both cases, the hydrogen is sticking at the back, and therefore they're on the same side across the carbon bond, and therefore, as you guessed it, this will be a cis configuration. And if you look at the next one, we have hydrogen sticking out on one and bromine sticking out on the other. So therefore, this one is now going to be a trans configuration. I hope this helped to clear out the idea behind cis and trans concepts. This can also work with amides, where the bond cannot rotate. So it will work with any of the compounds. The same idea works with any compounds where the bond cannot rotate freely because it's connected with at least 2 bonds between the same carbon, between the same elements. And therefore, that is what cis and trans isomers are about. I hope you liked this lesson. If you liked it, please hit like and subscribe to the channel.